All right, team, let's look at the third and final of the three experiments slash observations that screwed up the classical theorists. Well, didn't screw them. They're just like, how come we can't explain this stuff? So atomic line spectra, let's take a look. And I know you've probably seen this, and it's been known for a long time, where, if you take, say, if you've been to Las Vegas or a casino, you'll see the neon lights where they take these tubes with neon gas in there, put an electrical discharge, you get these interesting colors out. Or if you've ever been in a lab where you did these flame tests where you could take a salt solution like rubidium chloride or barium nitrate or something like that, and take a nichrome wire loop, heat it up and clean it, stick it in the solution of the ions, put it in a Bunsen burner flame, and you get these really interesting colors, right? It's a lot of fun. It's like magic. Well, when energy is absorbed by an atom or an ion, right? So it could be gas phase elements, it could be the ions in the solution, etc., etc. Whatever the source of energy is, right? Heat from a Bunsen burner flame, lasers, those are the fun ones, electric discharge, whatever. Energy goes in. Well, it turns out that energy absorbed can be re-released as light in many situations. All right, well, that's fine. What would classical theory predict, though? Well, since energy is continuous, right, all values are allowed, it's not discrete, like in the quantum situation, that would mean all energies or all wavelengths would be re-released, right, which would be white light. No, that's not what they saw. They got a really interesting emission spectrum, right? What's the different colors that were emitted after that energy was absorbed and then re-released as light or emitted? That's called an emission spectrum. Let's take a look at what we saw. And it was different for every element, and whether you did hydrogen, helium, krypton, whatever element it was, it gave a different type of emission spectrum. So let's just look at hydrogen. It's probably the simplest one, and let's take a real quick look at the experiment that allowed us to take a look at, hey, if we take a sample of hydrogen gas, put some energy into it, whatever that energy is, it absorbs it, re-releases it as light, all right? Well, what we see is a result of the mixing of all the colors that come out. So we need to separate those into individual wavelengths. So we need, like I said, something that can disperse that energy out, a prism, a diffraction grating, whatever. And then we need to take a look, have some kind of detector that can detect the different wavelengths or colors of light that come out. And we talked about in our first video when we did classical versus quantum theory, I think it was Bunsen and Kirchhoff that developed the first spectroscope, which allowed them to look through it and actually they could excite any gas phase element, right? The light was emitted, they energized it, usually with an electric discharge or something like that, or even in the Bunsen burner flame with ions, catch the outcoming radiation, that color we see, which is a mixture of all the wavelengths coming out, and with the spectroscope, they could split it up into the individual colors and actually see that. Kind of neat, huh? That's how they discovered rubidium and I think it was cesium or something like that. But let's draw a little more interesting design for how they were able to look at the individual colors or the atomic line spectra that these elements spit out, because they were expecting white light. That's not what they got. They got just a few different colors. They're like, what? That doesn't make any sense. Because if you only got a few different colors, that would mean the energies must be quantized or discrete. No. Okay, here's kind of an oversimplified view of what's going on. We can do this with any element, right? But let's just say we got some hydrogen gas, we input some energy, electric discharge, laser, whatever it is. But back in the day, probably an evacuated tube with some hydrogen gas and zap it up a little bit. Boom, it releases light. Whoa, and that light has a characteristic color to it. They would have expected white light. Nope. So what's going on? Let's say we got a slit so we can get, a nice focused beam of light, and have that light hit a prism or a diffraction grating or something like that. Now, obviously, different wavelengths are going to refract at different angles. So it comes in, right? The bluish purple colors tend to refract greater angles than the red, if you look into the mathematics. And so what comes out the other end are only a few wavelengths or a few specific colors, or a discontinuous emission spectrum, right? And classical theory expected all of them coming out. But no, for hydrogen, there's only 4 that they could actually see with their eyeballs in the visible spectrum. Of course, if there's some in the infrared or ultraviolet, they wouldn't be able to see those. So we'd have to detect those a different way. But they could see these and impinge that on a photographic film and you end up with what's called the atomic line spectrum. You can do this for all the elements, and they'd all be different. It's like a fingerprint for each element is different based on the energies. Well, they saw a red one at 656.3 nanometers, bluish at 486.1 nanometers, and a couple down the indigo violet range at 434.0 nanometers and 410.1 nanometers. That's it. That's all they saw. It tripped them out. They could not explain that because to the atomic line spectrum of hydrogen, if you use classical theory, it doesn't work. So what they take from this is if you get discrete wavelength values or colors coming out of the emission spectrum, that can only happen if the energies in that atom or ion were also discrete or discontinuous. No, but classical theory says it must be continuous. We have an issue. Houston, we have a problem. All right. So now we've got 1900 Max Planck proposing the quanta concepts and discrete energy values, quantized energies. We've got Einstein, right, proposing the photon concept, particulate matter of light. So now Niels Bohr can come along and explain this atomic line spectra, and he nailed it. Now remember, Balmer, we mentioned in our first video, classical versus quantum theory, Balmer tried to characterize this by fitting the data, right? So he knew the answer ahead of time. That's called an empirical approach. So he knew the data ahead of time. I'm not going to write Balmer's equation down. You could look up in the book. But Balmer forced an equation to fit so that he could get these as the answers. No theory behind it, anything like that. To get Balmer's equation, which showed that the mathematics, you had to have a quantized value in order to do it, like values of 1, 2, 3, 4, stuff like that. But nothing in between. You couldn't have 1.1 or 1.3. It had to be a 1, 2, 3, or 4. They use this term n in there. So let's take a look at what Niels Bohr said to try to explain this. And he only worked on hydrogen, and it just opened the eyes of a whole lot of people. Let's see what he did. All right, this one's easier to draw and show you, so let's get the verbiage out of the way first. All right, so 1913, Niels Bohr comes along. Remember, we've got 1900s out of the way with Max Planck, 1905s out of the way with Albert Einstein. So we've got the quantum concept. We've got the photon concept. He needed those in order to do this. And so he's got the Bohr model of the atom, commonly called the planetary model of the atom. You'll hear that all the time. Simply, it's not the most correct way to describe an atom, but it's the most simplistic way, I think. And I'll draw it in a second. But imagine... remember with Rutherford, with the nuclear atom, you have the nucleus with the protons and the neutrons, and then electrons moving around outside. Bleep, that was it. All right, so now what Bohr's trying to do is go, well, how does this atomic line spectra work? He's looking at some of Balmer's data going, wow, so based on that, we've got to have discrete energy values. So how does that work out? So he said, well, let's take the nucleus, kind of like the sun, and let's have the electrons moving around the nucleus in circular orbits, kind of like planets moving around the sun, if they moved in circular orbits, which they don't. But imagine they did. It's kind of that, but they can only be at set distances, right? So they move in these classical circular orbits about the nucleus. We'll talk about the classical problem with that. And he said those electrons are they have quantized angular momentum, right? Because as electrons moving, as it turns, it's got angular momentum, right? What's that? The mass times velocity or something like that? And they're discrete, so only specific values of angular momentum are allowed. When you look at the mathematics, the angular momentum relates to the energies of the electrons, so they have quantized energy values, and distances from the nucleus. We'll look at those in a little more detail. So these orbits can only be at specific distances from the nucleus, kind of like the planets are at specific distances from the sun, right? Moving around, moving around, moving around. And then what he allowed in here was that electrons can move from orbit to orbit. If they absorb some energy, they can jump from one orbit to another. Or if they release energy, they can drop from one orbit. If they drop from here to here, they can release energy, and those are the photons of light that we see. If they absorb energy, they get excited and they can move up to a different orbit. But there's only set values, right? They can either be here or here or here. So let's draw that. I think it's easier to see and talk about this quantized behavior. All right, let's take the more pictorial. It's easier, I think, when you look at it pictorially. So picture the planetary model. So the nucleus is like the sun. Then you got Mercury and Venus and blah, 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 blah. But here we got the nucleus. And we've got the first electron orbit, we'll call that n equals 1. Second electron orbit, n equals 2, n equals 3, n equals 4, blah, 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 all the way to n equals infinity, which would be an electron actually separated from the, if we'd like rip the electron off the nucleus, we'd call that n equals infinity, all right? So what Bohr looked at, he's got the electrons, so let's say we've got an electron here, and that's moving in circular motion around that. That's not really how it works, but that we'll find that out later. We'll have a better model in a little bit. That's classically how he looked at it. It's moving around. Now, the problem with that point of view, if you've got an electron moving in circles with angular momentum, it's losing energy as it turns. So classical theory says the electron should go boom, crash into the nucleus, because it should continually lose energy and then spiral and crash into the nucleus. Well, obviously that never happened because we wouldn't be here if it did. Atoms couldn't exist, right? So obviously he said, well, these electrons must have constant energy because they're obviously not crashing into the nucleus. So the quantized nature of the angular momentum gives them this constant angular momentum or constant energy. And since the distance from the nucleus relates to energy, there can only be specific distances, or think of it as a radius, a certain radius that they can exist. Nowhere in between. They can't exist here, only here, or, any integer, we'll call that n. We'll find out that's called the principal quantum number. And so from his mathematics, he looked at the distance from the nucleus, right? R, the radius, sub n, some integer, is equal to that integer squared times the Bohr radius, which is 53 picometers, right? So for n equals 1, well, 1 squared is 1, so the first electron orbit would be 53 picometers away. The second orbit would be n equals 2, which would be 2 squared, or 4 times 53. So 4 times 53 picometers, that would be where the second electron's distance is, moving around. So you can calculate the distance of these electrons from the nucleus using Bohr theory. Well, since the distance relates to the energy, right, he found that the energy at some principal quantum number, 1, 2, 3, 4, 5, you can't have 0, that'd be in the nucleus, right, is a negative some constant, capital R sub capital H, over the principal quantum number squared. And that RH is called the Rydberg constant, which is 2.179 times 10 to the minus 18th joules. So, at an orbit of n equals 1, at a distance of 53 picometers, well, 1 squared is 1, so the energy would be negative 2.179 times 10 to the minus 18th joules. The second orbit would be 4 times, that divided by 4, right? But negative. See that negative sign there? The reason it's negative is because at n equals infinity, that's defined to have an energy of 0. So let's write that up there. So we're defining an energy at infinite distance from the nucleus completely separated as 0. So as it gets closer, it's negative, the nucleus is positive, right? It gets higher and higher energy, right? Or lower and lower energy. Sorry, it's more attracted. So it's getting lower energy, it moves towards the nucleus. So it prefers to be in this first state, right? So as it gets closer to the nucleus, the energy gets less and less from 0, gets lower and lower, thus the negative sign, all right? So you could calculate those values very, very easily. So n equals 3. 3 squared is 9. Take 2.179 times 10 to the minus 18th joules divided by 9. Stick a negative sign in front of it. That's the energy level 3. All right. So what we're going to do, we're going to do a second video that we're going to talk about electron transitions and calculate the energetics of electron transitions. But in essence, what we're doing, we're saying, hey, if an electron's in orbit 1, and if it absorbs energy, right, for like we did for the atomic line spectra, or there's from a laser, electric discharge, whatever, boom, it can jump to one of these higher orbits. But only if the energy is equal to the energy difference between these orbits. Oh, so in the next video, we're going to calculate the energy. No, we could probably do it in this video. Let's calculate the energy difference between those orbits. Or if an electron, say in n equals 4, it can drop down to n equals 3 or n equals 2 and emit radiation for those particular orbits. All right, so let's take a look at that. All right, the way Bohr looked at it, he said, hey, say, here's our planetary model, our Bohr model. Let's say we've got an electron in the n equals 1 orbit, and it absorbs some energy and goes boink to the n equals 3. It doesn't actually go boink, but you get the idea. It goes to n equals 2 or n equals 3 or some other n value, depending on how much energy is absorbed. We call that process excitation, going from lower to higher, like climbing up a ladder, right? So if an electron absorbs energy, whatever the source, electric discharge, a photon from a laser, whatever it is, it promotes an electron from a lower energy orbit, lower n value, to a higher energy orbit. Remember, lowest energy is n equals 1, going to higher energy up to a value of 0 at n equals infinity. So if I went from here to n equals infinity, that would actually ionize the atom, because the electron would go bye-bye and give it a positive 1 charge. Hey, so we can calculate ionization energies using this. Ooh, we'll put it to the math in a little bit. I'll probably do an example on a separate video, because they're pretty lengthy calculations. All right, but that's called excitation. So in this case, if we went from n equals 1 orbit to n equals 3 orbit, that's an electron transition, requires energy, right? We're climbing the ladder. But the quantization part of this is the energy difference between these two orbits, which we can calculate using Bohr's information, that must exactly equal the energy of the photon if we did light coming in. So if I have a photon coming in, let's do a black photon. Not that we have black photons. So let's say we have I don't know what a photon looks like, so let's say this is a photon. Boom! Imparts momentum to the electron, bam, kind of like the photoelectric effect, except in the photoelectric effect, that electron's on the surface of a metal. Photon comes in, imparts momentum to it, boop, pops it off, right? In this case, it's not enough energy to pop the electron off necessarily. It just goes to a higher energy or excited energy state, right? Now, what happens when it's in that excited state, it doesn't want to be there, so that electron tends to go back down to a lower energy. Nature always wants to go to a lower energy state. So we'll do the exact same thing on another board, but the electron will go from a higher orbit to a lower orbit. We call that relaxation. Let's draw that. So for the opposite process, relaxation, let's say we're starting with the electron in some higher orbit, some higher energy orbit, we'll say n equals 3. And it drops down to a lower energy orbit, let's say n equals 2 or 1 or whatever. So when that electron from a higher energy orbit drops down to a lower energy orbit, higher n to lower n, that energy is released. The atom is going from a higher to a lower energy system. The difference between the difference in energy between those two systems is released, commonly as a photon. So it, poof, photon shoots out. This is the emission. That's called emission. So you get the emission spectrum, which is what I drew for the original atomic line spectrum. You could also do an absorption spectrum. You could hit a sample with white light and see what wavelengths are absorbed to go from lower to higher, or you could absorb the energy and let them release that energy and relax down and see what's emitted. All right. So you get very similar atomic line spectra, just kind of like a negative image of one another. So let's say we go n equals 3 to 2 transition. So that's going to release energy in the form of a photon. Boop! And that photon will have an energy exactly equal to the difference between those two orbits, which we can calculate using Bohr's math, right? So that's called an emission spectrum. Now, because that delta E is going to be negative, you're taking the final state's lower than the initial state, right? So you're going to have a negative energy change. Can't have a negative photon energy. That doesn't make any sense, right? So when you're dealing with relaxation, we use the absolute value of the energy change between the two orbits so that we can get a positive photon energy. Well, so if you end up with a negative photon energy, you realize where the boo-boo is, right? That delta E needs to be a positive value when you do it into mathematics. So this is your quantum restriction right here. The photon energy and the energy difference between those two orbits for that transition have to be exactly the same. You can't have an electron drop from n equals 3 to n equals 1.5. because it can't exist there quantum mechanically, right? It can only exist here, here, or here. You can't take an electron in orbit 1 and go to orbit 2.2. N can't be 2.2. It can be 1, 2, 3, 4, 5, 6, all positive integers up to infinity. That's the restriction. So what I want to do is take Bohr's energy value, right? Energy was negative Rydberg constant over n squared. Well, let's derive an equation for an energy transition. And then on the next video, we'll calculate it and look at the different types of transitions possible. Hey, let's do some derivation on the next board. Yay! I think you could put this together if you really wanted to. If we look at any electron transition, let's say we want to calculate delta E, which would equal the photon energy. Right? So in the next video, we're going to calculate that, calculate photon energy, and actually using Planck's equation, we could calculate the wavelength or frequency of photons absorbed or emitted, and even look at the color if it's in the visible spectrum. We could actually predict what colors, with specific wavelengths and colors, particular elements would absorb or release. Oh, interesting. So anyway, we know from Bohr's mathematics that the energy is negative RH over n squared, right on? Well, let's say we start here at n equals 3, that'd be our initial n, and we go to n equals 2, that would be our final n. Or we can start anywhere and go anywhere, it doesn't matter. But where you're starting is n initial, where you're ending is n final. Well, let's plug in the value for because the change in energy would be the final state minus the initial state, right? So the final state would be the negative Rydberg constant over n squared final minus negative RH over n squared initial. Final state minus initial state. Well, the Rydberg constant's a constant, so let's factor that out. Let's factor out the Rydberg constant. So we get the Rydberg constant times negative 1 over n squared final minus negative 1 over n squared initial, which minus negative is positive, right? That looks kind of weird, so commonly this is flipped. So let's just flip these two. So delta E will be RH times 1 over n squared initial minus 1 over n squared final. I'll always give you that equation. And that is Bohr's equation for electron transitions. Whoa, okay, isn't that interesting? So what Bohr did then is take this and calculate all of the predicted energies. He could calculate for hydrogen. He only did hydrogen with 1 electron. So we know the energies, plug in n equals 1, n equals 2 for different transitions. He could calculate all the energy changes for the hydrogen atom. Well, let's talk about what happened on that board. We'll actually do some calculations on the next video because they take a while. But let's show you what happens when he applied this to hydrogen. All right, so Bohr applied his mathematics to the hydrogen, a single electronic species, and bam-o-whammo, perfectly matched what was observed in experiment for the atomic line spectra, right? So we calculated the energy of orbit 1, orbit 2, orbit 3, subtracted them to get the delta H for like a 2-to-1 transition, a 3-to-1 transition, a 3-to-2 transition, all that stuff. And he nailed those 4 lines, the red, I think red, blue, indigo, violet, whatever, of hydrogen. Boom! And everybody's like, whoa! Quantum stuff works! Yeah! Nobel Prizes for everybody, right on? So he was able to exactly calculate from his theory. Balmer forced an equation to fit the known data, right? That's why he doesn't get all the kudos. Bohr created a theory based on quantum ideas from Planck and Einstein and developed an equation that worked. And turns out his equation was a little more fundamental than Balmer's, but they were very similar. But Bohr derived his from theory, right? That's why he gets the kudos. And what was interesting is when he applied this to any other single electron species or hydrogen-like species. So if we took helium with 2 protons, 2 electrons, and pop off an electron to get a helium cation, +1 cation, well, it's 2 protons but 1 electron. So its nuclear charge is 2 instead of a nuclear charge of 1. It has 2 protons instead of 1. So let's call Z the nuclear charge, number of protons. So lithium, 3 protons, 3 electrons. Get rid of 2 electrons, so it's lithium plus 2, theoretically. So 3 protons, 1 electron. It's a 1 electron species. Boom! This worked for it. He was able to calculate the atomic line spectra for it. But what he did is he adjusted the energy, right? Normally it's just the Rydberg constant divided by n squared with a negative sign. But if you put the z squared there, the nuclear charge or number of protons, times RH over n squared with a negative, then it worked. But we got one more board to go. When there was more than 1 electron, we had problems. Oh no. All right, to kind of polish this off before we get to the next video where we'll actually do some electron transition calculations and show some kind of the regions in there where Balmer fits in a little bit more. When Bohr applied these ideas, worked perfectly for hydrogen and other 1 electron species, but if he applied it to anything with 2 or more electrons or multi-electron species, no, why it didn't work? So he he had some ideas. He was the first one to jump in the pool, you know what I mean, and really start splashing around in there. He's the first one to really start hacking away with a machete through the forest, clearing a little trail that other people could follow. And he got the Nobel Prize for it, but his theory was not quite correct. It had some good traits to it, but it wasn't perfect. It had to be upgraded a little bit, right? And the reason it didn't work so great, because he kind of blended quantum ideas and classical ideas, right? He treated electrons as point particles, right? And he treated them moving around in circular orbits with quantized angular momentum. We're going to find out electrons don't move in circular orbits, and we can't really treat them as a point particle where we know exactly where it is. So it required a few more discoveries to really understand that more of a quantum behavior of electrons to get an upgraded model called the quantum mechanical model that we'll look at. So we'll do some calculations in the next video, and then we'll jump into some of these new discoveries and get into the quantum mechanical model, which we use, or what they call the wave mechanical model. It's going to get really weird, my friends. But anyway, he deserved that Nobel Prize because he really opened up the door and took these quantum ideas from Planck and Einstein and applied them to the atom in electron motion and was able to garner some success in there. So he deserves all the credit he had. So Bohr was like a major bigwig back in the early 1900s and stuff. And he helped a lot of other people with their thinking processes. All right, get out your calculators. Let's do some gnarly electron transition calculations. Oh, the meat and potatoes of this chapter, baby.